It's a clear morning, the kind where you can see for miles. The crew of United Airlines Flight 232 has been in the air for about an hour, cruising comfortably at 37,000 feet over Iowa. Captain Al Haynes has been flying for 33 years. He's seen storms, mechanical hiccups, close calls, nothing that ever made him genuinely afraid. Then, at 3:16 in the afternoon, there's a sound. Not the sound of an explosion exactly, more like a thud, a deep, hollow bang, followed by a vibration that runs through the entire aircraft. Haynes looks at his instruments, then he looks again, because what he's seeing doesn't make sense. The hydraulic pressure, all three independent systems, is reading 0. Every control surface on that plane, the rudder, the elevators, the ailerons, gone. Unresponsive. A fully loaded DC-10 with 296 people on board, traveling at nearly 300 miles per hour, and the pilots have effectively no way to steer it. What happened next didn't just make headlines, it changed how every airline in the world trains its pilots. And it exposed a flaw in aviation design that nobody wanted to admit was real. By 1989, commercial aviation had already been through its most turbulent decades of learning. The jet age had brought speed and scale, but also a new category of disasters. Accidents that revealed how complex systems could fail in ways their designers never imagined. The Douglas DC-10 was one of the most ambitious aircraft of its era. Wide-body, 3-engine, designed to carry hundreds of passengers across continents. Airlines loved it for its range and capacity. Passengers mostly didn't think about it at all, which is exactly what you want. You don't want passengers thinking about the plane. Flight 232 departed Denver at 2:09 p.m. on July 19, 1989, bound for Chicago. It was an ordinary Tuesday afternoon, families going home, business travelers with laptops and briefcases, a group of Marines, children flying alone for the first time. The plane was fine. The crew was experienced. The weather was clear. There was no reason, by any reasonable measure, for anything to go wrong. Here's what nobody fully appreciated about the DC-10 at the time, or really about any commercial aircraft. The hydraulic systems that control a plane's flight surfaces were designed with redundancy in mind. 3 separate systems, using separate fluid lines, separate pumps. If one failed, another took over. If 2 failed, the third was still there. The engineers had run the numbers. The probability of all 3 systems failing simultaneously was considered so small that it was, for practical purposes, dismissed. What the calculations didn't account for was a single point of failure. One component whose destruction could cascade into all 3 systems at once. That component was the tail-mounted engine. And on Flight 232, it was about to become the center of one of aviation's most harrowing puzzles. The fan disc inside the number 2 engine, the one mounted at the tail, had developed a fatigue crack during manufacturing. A tiny crack, invisible to the inspection methods being used at the time. Over years of operation, and that crack had slowly, quietly grown. And on that Tuesday afternoon over Iowa, it reached its limit. The disc shattered at rotational speeds of thousands of RPMs. Fragments tore through the tail section with enough force to sever all 3 hydraulic lines. Lines that, by design, were routed through the same area because that's where the tail engine was. The redundancy that was supposed to save the plane was compromised by a single catastrophic event. The fatigue crack in that fan disc didn't appear out of nowhere. A year earlier, a similar disc had been flagged during inspection at another carrier. There were ongoing discussions in the industry about inspection intervals, about the reliability of existing detection methods. Ultrasonic testing, the standard at the time, had limitations. It could miss certain crack orientations depending on how the probe was angled. Some engineers had raised concerns. The paperwork existed. But the culture of the industry at that moment was one of high confidence. Fatal accidents in commercial aviation had been declining for years. The systems were working. The math looked good. Nobody was ignoring warning signs out of malice. They were operating within a framework that felt solid, because most of the time it was. The problem with low-probability catastrophic failures is that they almost never happen until they do. Back on the flight deck, Captain Haynes and First Officer William Records are working through something that has no procedure in the manual. There is no checklist for total hydraulic failure. It wasn't written because it wasn't considered survivable, or even meaningfully possible. But a piece of luck enters the picture. Dennis Fitch, a United Airlines DC-10 flight instructor, happened to be deadheading in the passenger cabin that day, flying as a passenger on his way to another assignment. A flight attendant tells the cockpit there's a pilot on board. Haynes gets him up front immediately. Fitch crawls to the throttle quadrant and begins manually working the 2 remaining engines, the only means of control they have left. By varying the thrust between the left and right wing engines, they can induce turns. It's crude, it's exhausting, and it only sort of works. The plane keeps pitching and rolling in ways that none of them can fully predict or correct. They have approximately 44 minutes from the moment of engine failure to impact. Here's what's remarkable about what was happening on that flight deck. These 4 men, Haynes, Records, Fitch, and Second Officer Dudley Dvorak were solving a problem in real time that had never been solved before. They weren't following a procedure. They were inventing one, mid-air, while managing a dying aircraft and trying not to let the crew and passengers see the full picture of how bad it was. Meanwhile, on the ground, air traffic controllers at Sioux City were scrambling. Emergency services were being called in. The airport was clearing runways. People were watching a plane on radar making slow, wobbling circles over Iowa, and everyone who understood what they were looking at knew that the math of survival was not good. The plane was losing altitude constantly. The crew had managed to aim it roughly at Sioux Gateway Airport, but aimed is a generous word. They had no real control over the approach, no way to adjust speed, no way to level the wings precisely. They were guiding a 200-ton aircraft toward a runway using only engine thrust, praying that close enough would be enough. At 4 p.m. local time, Flight 232 appeared on the horizon at Sioux City. It was not a normal approach. The plane was rocking side to side, dropping too fast, coming in too hot. The landing gear was down. That was something. But as it crossed the runway threshold, the right wing dipped sharply. The wingtip struck the runway first. The plane cartwheeled. The right wing sheared off. The tail section broke away. The fuselage tumbled, rolled, caught fire. One section of the cabin inverted completely. Cornfields adjacent to the runway were covered in burning wreckage. And then, silence. Emergency crews who had been staged for half an hour arrived in seconds. They expected to find no one. Instead, they found survivors. 185 of them. 111 people died. A number that is devastating and real, and must be said plainly. But 185 people walked, crawled, or were carried out of wreckage that had no business producing survivors. Entire sections of the fuselage had held together. Seatbelts had done exactly what they were designed to do. The seating configuration and the way the plane broke apart had, in some sections, protected the people inside. Human impact. Among the survivors was a passenger named Jerry Schemmel, who pulled a toddler from the wreckage that day, a little girl who had been separated from her family in the chaos. He didn't know her. He just heard a sound, followed it through smoke and debris, and brought her out. There were flight attendants who kept their composure through the entire descent, instructing passengers on brace positions, answering questions calmly, doing a job they had never truly trained for, because nobody had ever expected to need this training. Captain Haynes, when asked later how he felt about what had happened, was careful. He credited his crew. He credited Fitch. He credited the emergency workers in Sioux City. He acknowledged the people who didn't make it, by name and in full. He never positioned himself as a hero, even as everyone around him did. The investigation began within hours. The NTSB collected every piece of the shattered fan disc they could find from the Iowa cornfields and reconstructed it like a three-dimensional puzzle. The fracture origin was identified. A small titanium void, a metallurgical defect invisible to the inspection methods in use, had allowed the fatigue crack to start. The crack had been growing for years. The disc had been inspected. Nothing had been flagged. The entire aviation industry was now looking at the same finding and asking the same question. How many other discs right now are carrying defects that nobody can see? The consequences were immediate and far-reaching. The FAA ordered inspections across the entire fleet of aircraft with similar engine designs. Manufacturing standards for high-stress rotating components were elevated. Inspection methods were overhauled. Fluorescent penetrant inspection, improved ultrasonic techniques, new protocols for tracking parts through their entire service lives. Beyond the hardware, something else changed. The concept of crew resource management, CRM, had existed before Flight 232, but this accident gave it a different kind of weight. Haynes and his crew had survived in part because of how they communicated. Haynes had listened to Fitch. He had asked for input. He had made decisions collaboratively rather than unilaterally. In the culture of aviation at the time, captains were expected to be singular authorities. This accident demonstrated, in the clearest possible terms, that hierarchy can kill you when the problem is bigger than any one person. CRM training became standard. Airlines began treating the cockpit as a collaborative environment rather than a chain of command. It would be comfortable to think of Flight 232 as a story from another era. Older planes, older inspection methods, a problem that has since been fixed. But the lessons from that afternoon in Iowa are still being applied, and in some cases, still being learned. The idea that redundant systems eliminate catastrophic risk is one that keeps reappearing across industries. It showed up in the Deepwater Horizon disaster, where blowout preventers failed in ways that redundancy wasn't designed to handle. It shows up in software infrastructure, where cascading failures take down systems that were supposed to be independent. It shows up anywhere that humans design for the failure they can imagine, and then encounter the one they didn't. The specific defect that destroyed Flight 232, a titanium void in a fan disk, is the kind of failure that modern inspection methods are far better equipped to catch. But the broader lesson about what happens when a single point of failure intersects with a system designed around multiple independent backups is perennial. It's also worth noting that Flight 232 fundamentally changed how pilots are trained for emergencies that have no procedure. Simulators now run scenarios that are designed to be unsolvable by the book. Scenarios where crews have to think, collaborate, and improvise. The scenario used most frequently? Total hydraulic failure in a DC-10. Because if it happened once, the question isn't whether something like it could happen again. The question is whether the people in that cockpit will know what to do. 1. Redundancy only works when redundant systems are truly independent. Routing 3 hydraulic lines through the same physical space was a design assumption that looked solid on paper and proved catastrophic in practice. Every complex system has assumptions like this. The dangerous ones are the assumptions nobody is checking. 2. Low probability is not the same as zero probability. The math said total hydraulic failure was essentially impossible. The math was wrong because the math didn't account for a single catastrophic failure mode that hadn't been imagined. Unknown unknowns don't show up in probability calculations. 3. Survival under catastrophic failure is rarely the product of one person's heroism. Haynes said it himself. He couldn't have done it alone. The outcome of Flight 232, 185 survivors where none were expected, was the product of a crew that communicated, a community that prepared, and a set of decisions made well under conditions that would break most people. 4. Every safety standard in aviation is written in the specific language of what went wrong before. The improvements that followed Flight 232 in materials inspection, crew training, and emergency protocols exist because 111 people did not survive. That's not a comfortable thought. It's meant to be uncomfortable. There's a photograph taken in the cornfields near Sioux Gateway Airport on the evening of July 19, 1989. Scattered wreckage as far as the eye can see. And amid the debris, intact seats still in their rows with seat belts still fastened. Captain Haynes spent years speaking publicly about the crash, not to be remembered, but because he believed that the people who didn't walk away from that cornfield deserved to mean something beyond the accident report. He wanted the lessons to outlive the headlines. He was right to push for that, because the safest skies in history didn't arrive by accident. They were built incrementally on the precise record of what had gone wrong before, and on the refusal to let those failures become footnotes. Safety isn't a destination you arrive at. It's a discipline you maintain, one uncomfortable question at a time.